We have a moment to pull this up. All right, everybody can still see the screen properly? All right.
Yep.
Okay, good afternoon, everybody. Welcome to the first seminar of our 2023 spring series. Today is February 2nd, and we're going to be hearing a talk from Dr. Zhu. First, to introduce our leadership team, we're across all of the Gallagher College of Engineering. This year, Roshan and I are the co-chairs. We have our publicity team, which is currently made up of Andrew and Avinash, and a very large support team this year, made up of Anirban, Swapnil, Mayank, Mohammed, Fulani, Nurian, Suraj, Michelle, and Latif, and also our regular advisor, Dr. Farouk Mistry. If you would like to join the graduate student community, we hold regular meetings on Wednesdays at 5:45 p.m. this semester, although we are open to moving them if more people can make a better time. If you would like to attend the meeting, please email either me or Roshan. Our email addresses are up here. And if you would like to become a member, we do encourage you to join our Engage page. You can do that by scanning this QR code, which I can post up here for a little bit. And that way we have also a record of attendance for everybody who's part of the GSC. We do also have a Facebook page, which is updated with when we're having meetings and previous events that we've had and upcoming ones. And also we do try to record as many of our lectures as we can. All of those will go up on our YouTube page. So if for some reason you have to leave due to a class or a conflict, or you can't make a talk, we do post all of these so you can watch it later. For AME students and anybody in that building, and really anybody in GCOE, we do also have a team room, which is available for you to use, which is somewhere you can kind of chill out and do work. We have whiteboards, coffee pots, microwave. Just email us if you would like access. Just a reminder, after I'm done with this introduction, we'll be posting a sign-up sheet, and we do encourage everybody to sign that so that we know exactly how many people are attending. Now, today we'll be hearing a talk from Dr. Zhu, who just recently joined OU this semester. Prior to that, he was a postdoctoral scholar at the University of California, Santa Barbara. He obtained his PhD and master's from the Georgia Institute of Technology and a master's from the China Academy of Engineering and Physics, and has a bachelor's from Beihang University. Now, he's authored and co-authored one book chapter and more than 80 journal articles, and has received awards such as the Materials Research Society Graduate Student Award Silver Medal and Georgia Tech Sigma Chi Best PhD Thesis Award. So with that, I'm going to go ahead and pass this over to Dr. Zhu.
Hey, great. Let me share my screen, and thank you, Rachel, for the introduction. Okay. I believe now you can see my screen, right? But there is no slide there. Let me.
You can see the screen, but no slides yet.
Okay. So can you see my slide now?
Yep, you're good.
Okay, good. Hello, everyone, and thank you, Rachel, again for the introduction. It is a great honor to virtually be with all of you. The societal need for reduced emission and the increased energy efficiency are driving the development of an advanced structural material in two directions. One is the low temperature application, such as the lightweight materials for transportation. Another is high temperature application, such as the heat resistant materials for a nuclear reactor and a jet engine. And important type of structural material is metal. About 3/4 of all known chemical elements are metals. 7 of the 10 most abundant elements in the Earth, the crust, and are metals. Metals are excellent structural materials because of their exceptional mechanical and thermal properties, as well as the cost effectiveness and sustainability. So many metals can be produced by additive manufacturing, which join the material layer upon layer to make an object from 3D model data. One of the metal additive manufacturing methods is the powder bed diffusion. At the smallest length scale, the surface of the powder absorbs the laser and melts. Then the melt would flow on the surface of the powder bed and then solidify. In the meantime, we need to feed a new powder to the next layer. There are several challenges in the field of additive manufacturing. First, the process is highly multi-physics. Second, most additively manufactured metals have microstructures very different from those produced by conventional means. So it is hard to predict their mechanical properties based on microstructure. And at the part and the component level, the topology is very hard as well. So to address the challenges, we need to understand the processing structure property performance relation. In the context of additive manufacturing, an example of the processing structure relation and include laser powder and interactions, melting, and solidification. And examples of the structure property relation and include strengthening, deformation, and failure. And examples of the property and performance relation and include a topology and optimization and uncertainty quantification. So in my previous research, I mainly focused on the structure property relation, at the core of which are deformation and the failure. So how do metals deform and fail? Well, there are two main ways: the plastic deformation and the fracture, which are sometimes related to each other. The plastic deformation occurs in ductile materials and can have four mechanisms and in crystal. The dislocation slip, training, phase the transformation and amorphization. In the meantime, a fracture can occur in both the ductile and brittle material. And ductile fracture occurs after large plastic deformation, while a brittle fracture occurs after small or no plastic deformation. So in my previous research, I mainly focused on the dislocation slip. So what is that? And A dislocation is a 1D line defect in a crystal. It has two main properties: the line direction L and the Burger's vector B. The angle formed between L and B is the character angle of the dislocation. When the angle is 0, it is a screw dislocation. When the angle is 90 degrees, it is an edge dislocation. When the angle is between 0 and 90 degrees, it is a mixed type for dislocation. So the motion of the dislocation controls the plastic deformation of the crystal, and the interaction between the dislocation and the defect, such as the grain boundaries in the movie on the right, determine the strength of the crystal. That is why the dislocation play a very important role in deformation and the failure of the ductile crystal. So materials are multi-scale systems. Their structure and behavior span over multiple lengths and the time scale. But at each scale, there is at least one method to model the dislocation. At the electronic scale, we can use the density function theory calculation. The simulation cell usually contains less than 5 with dislocation. At the atomistic scale, we can use the atomistic simulation. The simulation cell usually contains less than 20 dislocation. At the micro scale, we can use either the discrete dislocation dynamics or the phase field dislocation model. The simulation cell can contain up to 1,000 the dislocation. At the macro scale, we can use the crystal plasticity method. The simulation cell can contain up to 1 billion dislocation. So as we move up the scale ladder, the computational model would have a higher efficiency, but a lower accuracy. In the meantime, these models were originally designed for individual length and time scale. They do not talk to each other. One way to strike a balance between the efficiency and accuracy is to link the different models, and that is multi-scale modeling. So there are two types of multi-scale modeling: concurrent modeling and sequential modeling. The concurrent multi-scale modeling is preferred for systems with spatially varying resolution. It partitions the system into 2 or more domains. In each domain, we use a different method. Some methods have higher resolution and the calculations are slower. Other methods have lower resolution and the calculations are faster. Since all the domains are in the same system, they must not evolve at the same time. This means that the faster domain must wait for a slower domain. In sequential multi-scale modeling, we first run a slower simulation at a lower length scale. Then we use their output as the input for the faster simulation at the higher length scale. Unlike the concurrent modeling, calculation at the the different scales in sequential modeling are done separately, and the information only flows one way from lower length scale to higher length scale. My research so far focuses on multi-scale simulation at 3 lengths and the time scale. I work with both concurrent and sequential multi-scale modeling. I will first talk about concurrent multi-scale modeling, for which I use a coarse-grained atomistic method. All coarse-grained atomistic method partition the material system into 2 domains. On the right-hand side is the atomistic domain. It allows for lattice defect, but has a high computational cost. On the left-hand side is the coarse-grained domain, which consists of pseudo an atom or phyllite elements. Within each element, no lattice defect is allowed. The advantage of the coarse-grained domain is its no computational cost. In this figure, there is an edge dislocation in the atomistic domain on the right-hand side. But what if it moved from right to left, trying to enter the coarse-grained domain? In this case, most coarse-grained atomistic method would need to define the phyllite element back to atom to allow the dislocation to glide through. But that would be computationally expensive. In my work, I use a concurrent atomistic continuum method, which split the phyllite element into 2, accommodate the dislocation. This method has a name. We call it CAC. And compared with other method, a CAC is much more computationally efficient. So how does a CAC work? In the atomistic domain on the left-hand side, everything is the same as in an atomistic simulation. And that is, we first obtain the forces on the atom. Then we use them to update the position of the atom. At the next step, we calculate the new forces on the atom. In the coarse-grained domain on the right-hand side, however, we put 1,000 of atoms together to form the phyllite element. In each element, we first obtain the forces on the integration point. Then we calculate the forces on the nodes. Then we use them to update the position of the nodes. Then by linear interpolation, we obtain the new position of the integration point. At the next step, we calculate the new forces on the integration point. As a result, the CAC simulation can be 2 to 3 orders of a magnitude faster than atomistic simulation. Because we want to allow for the the dislocation in the coarse grain, the domain, we use a 3D rhombohedrophyllite element with all the surfaces on the slip plane of the lattice. So in FCC lattices, the element surfaces are on one plane, but in BCC lattices, they are on one O plane. The edginess of the calc simulation cell can be up to 6.5 micrometer. The largest calc model so far is equivalent to more than 10 billion atoms. There are two ways to run calc simulation. The first way is to use the PyCalc, the Python scripted calc simulation in environment. To help other researchers use this code, I built a website to host its user manual. Since I launched the website in 2017, it has been visited by researchers from more than 70 countries. Recently, calc was implemented into LAMP, the most popular open source atomistic simulation software in the world. So another way to run calc simulation is through LAMP. So calc is particularly useful in modeling the dislocation defect and interaction. Since these interaction determine the strength of a material, calc simulation results can help with material design. The idea is that the lattice the defects are located in an atomistic domain, while everywhere else we use a coarse grain domain to accommodate the propagation of a multiple dislocation. So within the atomistic domain, there can be any lattice defect. In my previous research, the defects have been obstacles, stacking fault, and a grain, and boundaries or biomaterial interfaces. I will now talk about them one by one. The first example concerns the dislocation obstacle interaction in a luminance. We aim to answer two questions. One, how does the interaction mode differ and for different types of an obstacle? And two, how does the interaction mode change with the number of the dislocation? In the movie on the left, a 5-edge dislocation sequentially share a void. In the movie on the right, the void is replaced with a strong precipitate, and all these locations go around the precipitate instead of sharing it. The main finding is that the dislocation precipitate an interaction follows an oscillating on order one and Hertz looping mechanism. Specifically, the first dislocation bypass follow the order one looping mechanism. Then the second, the dislocation bypass follow the Hertz looping mechanism, and then the third, the dislocation bypass again follow the order one looping mechanism. As a result, there can be no more than one shear loop around the precipitate after any number of the dislocation bypass, and this has changed our understanding of obstacle strengthening of material. So the the next example is the dislocation stacking fault interaction in an aluminum nickel and silver. So there are two types of stacking fault. One is the intrinsic stacking fault, which involves 140 the plane. Another is the extrinsic stacking fault, which involves 240 the plane. And our goal here is to understand how the interaction mode the changes for different types of stacking fault in different materials. For the intrinsic stacking fault, we find that the screw and dislocation cuts through it and in nickel, lysis in aluminum and transformed it into an extrinsic stacking fault in silver. For the extrinsic stacking fault, we find that the screw dislocation cuts through it in aluminum and transformed it into an intrinsic stacking fault in nickel, while transformed it to a three-layer twin in silver. The different interaction modes are due to the different fault and energies and their ratios in the three FTC metal. So the third example is the dislocation grain boundary and interaction in nickel. Our goal here is to understand how the interaction mode, the changes with the different types of grain and boundaries. So in the movie on the left is the sigma 3 111 coherent twin boundary. In the movie on the right is the sigma 11 113 symmetric tilt grain boundary. So the main finding here is that all 5 screws dislocation cuts through the sigma 3 twin boundary, while they glide and within the sigma 11 grain boundary instead of cutting through it. So this suggests that the sigma 11 boundary is the stronger barrier to dislocation motion and may strengthen the material more significantly. So the fourth example is the dislocation in the bimetal interface and interaction. So we consider 2 types of interfaces. One is between nickel and the copper. Another is between copper and silver. We want to understand how the interaction mode the difference between the 2 interfaces. So we first find that even before the dislocation actually interact with the interface, the non-range stress field of the dislocation pile up with the cause the evolution of interfacial misfit dislocation, and the evolution is more pronounced in the nickel copper interface than in the copper silver interface. Then upon the dislocation interface, the interaction, we find that the copper silver interface is a stronger barrier to dislocation motion than the nickel copper interface. That is mainly because the copper silver interface has a higher interfacial misfit dislocation density. In addition to metal, I also use the CAX to study semiconductors. Here is a silicon germanium bilayer. The first, we find that there are 3 types of interfaces differing in interfacial misfit dislocation network. And all these 3 interfaces have been observed in experiment. Similar to the previous slide, we want to understand how the interaction mode differed among these three interfaces. We then let 460-degree mixed type to dislocation move towards the interface. We find that the type 3 interface is a stronger barrier to the motion of the dislocation than the other two types. This is because the type 3 interface has the highest misfit dislocation density. This suggests that to have a strong silicon germanium bilayer, we may want to form type 3 interface between the silicon layer and the germanium layer as much as possible. I'd like to emphasize that small scale at a mystic simulation could only consider one dislocation in each of those problems. My work was the first one that considered multiple dislocation and interaction with various types of the defect. So these large scale simulation are way beyond the capability of the typical classical and atomistic simulation. In addition to the dislocation defect and interaction, I also use the CAC to study fracture. So the idea is that the entire system is modeled by across the domain, except around the crack, which is modeled by an atomistic domain. So as I mentioned earlier, there are two types of fracture. The ductile fracture occurs after large plastic deformation, while the brittle fracture occurs after small or no plastic deformation. In my previous research, I used the CAC to study both of them. So here I show an example in copper. So I pull the top and the bottom layer of the system away from each other to simulate the mode 1 fracture. When the finite element in front of the crack tip is not refined, there is a strong stress concentration at the crack tip, and the crack is stuck. Defining the element to atom would reduce the stress, the concentration, and allow the crack to propagate. So with that in mind, I track the position of the crack tip and adaptively define some finite elements to atoms. So we found that the crack could propagate and without the dislocation nucleation, suggesting that this is the brittle fracture. The displacement curve predicted by CAC is similar to that by equivalent molecular dynamics simulation. So if I change the lattice and orientation of the system to one that favor the dislocation nucleation, the brittle fracture would become the ductile fracture. And again, the entire system is modeled by a coarse-grained domain except around the crack. And unlike the case of the brittle fracture on the previous slide, here, as the crack propagate, the dislocations are also nucleated from the crack tip. And this phenomenon is well captured in the CAC simulation with the help of the adaptive element refinement. So for the same loading rate, the displacement curve are similar in CAC and in MD simulation. The advantage of using CAC is that with the same number of processors, it took over a month to finish the MD simulation, while it only took 2 days for the CAC simulation. So I have talk about the concurrent multiscale modeling using the CAC method. Next, I will talk about sequential multiscale modeling. At the electronic scale, I conduct a density functional theory calculation. Then I use the results to inform atomistic simulation at a higher length scale. Then at an even higher length scale, results from the two lower scale calculations are used to inform a phase field the dislocation model. So combining everything, we essentially have a sequential multiscale modeling framework. This framework can be applied to any ductile crystal. Here, I will talk about its an application to a multi-principal element, an alloy and a metallic laminate. So first, what is a multi-principal element alloy? So the multi-principal element alloy, MPA, are alloys in which two or three or more principal element form stable and solid solution phases on simple underlying lattices. And this is in contrast to traditional dilute an alloy in which one principal an element formed the matrix with a small amount of other elements added. So here I focus on a refractory metal whose melting points are higher than 2,200 degrees C. In a jet engine, the temperature can be up to 2,000 degrees C. So refractory metals can withstand high temperatures without melting. However, the strength of pure refractory metals with the decrease rapidly with an increasing temperature. At about half the melting point, their strengths are near zero. But if we mix up several refractory metals to make an MPA, there would exist a strength a plateau at about half the melting point. The alloys are called refractory MPAs, and they can retain an excellent properties at high temperatures. So in this talk, I will focus on one specific alloy that is made of an equimolar and molybdenum, niobium, and titanium. At the electronic scale, I conduct the density function theory calculation. First, I calculate some basic structural parameters and then compare them with the experiment. Next, and I calculate the general the generalized stacking for an energy, which is the local an energy required to shift half of the crystals with respect to the other half. So in the bulk material, the three chemical equaniments are equal molar, but locally they are not. So the local an energy would depend on the local chemical composition. For example, if there are more molybdenum an atom or a fewer niobium atom, the stacking for the energy would be higher. So we then use the density functional theory and calculation data to build an interatomic potential, which is fundamentally important to at a mystic simulation. So we chose a machine learning based moment tensor potential because it has an excellent balance between the accuracy and the efficiency. In this potential, the atomic energy is expanded through a set of moment tensor function of the local atomic environment. The data of both the pure metals and the anodes are used. The potential is then optimized using a polynomial regression. About 90% of the data points are used to train the potential, and about 10% to test it. So with the interatomic potential in hand, I conduct at a mystic simulation at a higher length scale. So I built a simulation cell that contains a short dislocation. The slip plane can be 110, 112, 123, or 134 plane. I then calculate the local slip resistances of the dislocation. We find that in pure metals, the local slip resistances on the two highest order planes are higher than that on the low order 110 plane. However, in molybdenum titanium, the opposite is true. So this is unexpected. On the other hand, these slip resistances are local and valued based on short dislocation. So how about the slip resistances of the long dislocation in a bulk material? So to answer that question, we use the phase field dislocation model to calculate the slip resistances of the long dislocation in both pure niobium and molybdenum titanium. The dislocations are initially straight, and in niobium it remains straight and when gliding. However, in molybdenum titanium, the dislocation becomes wavy. That is because each point along the dislocation line experiences a different local slip resistance. We further find that the slip resistance in the molybdenum titanium is higher than that in pure niobium. This suggests that the anode is stronger than pure metal. We also find that even in a bulk MPA, the slip resistances on higher order, on the 1, 2, 3, and 1, 3, foreplane are still lower than that on the low order 110 plane. However, these results are for the dislocation lines only. So how about the dislocation loops? So we then use the phase field, the dislocation model to calculate the slip resistances of the dislocation loop in both pure lyobin and moly-lyobin titanium. So first we see that the dislocation loop expands uniformly in lyobin, but not in moly-lyobin titanium. We also find that similar to the dislocation line, the slip resistances of the dislocation loop on higher order planes are also lower than that on low order 110 plane. So all the results are very intriguing. And however, they are solely based on simulation. And naturally, one may wonder if these are real at all. So my colleagues at UC Santa Barbara performed the institute tensile screening in scanning transmission electron microscope. They found that the dislocation tend to glide on 112, 123, and 134 plane, but rarely on the 110 plane. This verified our simulation results and confirmed that the plastic deformation in moly-lyobin titanium indeed occurred by multi-planar slip. So then based on both computational and experimental results, our joint paper was published in Science in 2020. So in addition to refractory MPAs, the phase field, the dislocation model has also been used to a non-refractory MPA. And this one is made of cobalt, chromium, iron, and manganese, and nickel. So we divide the simulation cell into many regions and assign the different generalized stacking for the energy to different regions. By varying the mean region size and the mean GSFE, and we carried out 83 phase field simulation. We found that both the region size and the GSFE affect the critical stress for the dislocation glide. However, we were not able to quantitatively understand those effects because there were so many inputs and outputs. So one way to link the input and the output is the machine learning. So we use the Gaussian process regression and an algorithm that is implemented in scikit-learn. So we use 75% of the data to train the machine learning model and 25% for the test. So we find that the mean GSFE affects the critical stress for the dislocation glide much more than the mean region size does. Therefore, to achieve MPa with high critical stress, and we mainly need to change the mean GSFE from the perspective of the anode design. So in addition to MPAs, I also apply I've also applied the sequential multiscale modeling framework to metallic laminate, which are assemblies of well-oriented laparoscopically thin and oscillating metallic layer. There are three types of interfaces in laminate: coherent, semi-coherent, and incoherent. The interfaces control the property of laminate. One type of laminate is made of copper and niobium. It has an exceptional strength and thermostability compared with pure copper and pure niobium. So there are two types of an interfaces: a 2D sharp interface and a 3D interface. So the copper niobium laminates containing 3D interfaces that have a higher yield stress than those containing 2D interfaces, and the two have comparable ductility. Compared with the 2D copper niobium laminates, the 3D laminate has an additional geometric parameter, the interface, the thickness. That is the effect of both layer thickness and the interface, the thickness on mechanical property of 3D laminate is uncostly and time-consuming in experiment. So I use sequential multiscale simulation. So we know that copper is an FCC crystal, while niobium is a BCC crystal. The 3D interface is a mixture of copper and niobium. So it could be a crystalline or amorphous. To determine the stable phases of the 3D interface, we first conduct atomistic simulation to calculate the cohesive energies of three phases: FCC, BCC, and amorphous, for each anode composition between pure copper and pure niobium. By comparing the cohesive energies among the three phases, we find that when the anode contains more than 75% of copper, it is an FCC crystal. When it contains less than 15% of copper, it is a BCC crystal. For composition in the middle, the copper niobium anode is amorphous. Then I use the phase field, the dislocation model, to study the slip transfer of dislocation across the 3D interface. So this problem is very important because the slip transfer process controls the yield stress of the laminate. I considered the two cases. In case A, the dislocation is initiated in copper and ends in niobium. In case B, it is the other way around. In each case, I vary the interface, the thickness from about 1 nanometer to 20 nanometer. I found that one, the critical stress for the slip transfer is higher for a 3D interface than a 2D interface. And two, the critical stress and increases with the interface thickness until about 15 nanometer. And after that, the critical stress and approach a constant of 2.1 gigapascal in case A and 1.9 gigapascal in case B. In the meantime, my colleague at the University of Minnesota conducted an institutional micropinner compression experiment. They found that when the copper nylobin laminate containing 3D and interfaces yield, a sharp shear band is formed, and the yield stress is 1.9 gigapascal, which is close to the prediction of the phase field the dislocation model. So then based on both the computational and experimental results, our joint paper was published in Nano Letter last year. So to recap my research to date, I worked on both concurrent and sequential multiscale modeling as well as machine learning. Using these methods, I studied a series of the plastic deformation and fracture problem in a wide range of structural materials. My simulation results have been verified by institute experiments. Overall, a multi-scale simulation and machine learning are very useful because they can provide the information not easily and accessible in experiment. For example, the density function theory calculation works at terms and the time scale are smaller than high resolution GEM. So those scales are particularly important for an alloy such as MPEA. So now I want to talk a bit about my current research at OU. So I'm now the PI of the computational materials mechanics and manufacturing lab. The vision of our lab is to use the computational approaches to guide the design and manufacturing of high performance structural and functional materials. My lab works at the intersection of material mechanics and manufacturing. We focus on multi-scale, multi-physics simulation and the data-driven methods such as machine learning. In the meantime, we collaborate with experimentalists. My current research at an OU is based on my previous research. So I'm making 4 extensions. The first extension confirmed the norms and the time scale of the objects in my research. My previous research focused on electronic scale atomic scale and micro scale. Now I am expanding my modeling efforts to the macro scale. For example, I'm working with the crystal, the plasticity method, the finite element analysis, the discrete element method, and the phase transformation modeling. Another an extension concerns the portion of my effort on the multi-scale simulation and machine learning. In the past, I worked more with multi-scale simulation and less with machine learning. Now I am spending half of my effort to each of them to make a better use of both methods. The basic idea is that when there are limited data, but a lot of physics, I use the multi-scale simulation. On the other extreme, where there are a lot of data but limited physics, I use machine learning. If the case is somewhere in the middle, I combine the two approaches and use the physics-informed machine learning. The third, the extension concerns the content of my research. In the past, I worked mainly on structural materials. Now I am studying functional materials as well, with a focus on how mechanical failures such as fracture and delamination would affect their function and performance. The last extension also concerns the content of my research. In the past, I worked mainly on the structure property relation, and now I have evolved the processing and then studying the processing structure property relation. For example, my research can support additive manufacturing of materials. At the lateral scale, I study the laser matter interaction. Then at the micro scale, I model the microstructural evolution during melting and solidification. Lastly, at the millimeter scale, I predict the macro scale material property from the microstructure. Specifically, my lab is working on two types of materials. The first one is the chemically complex materials. In terms of the mechanical properties, these materials have high strength at high temperatures, an excellent toughness at low temperatures, and elevated the damage resistance. They have an application in a jet, an engine, high latitude, the vessel, and the nuclear reactor. The second type of material is structural complex material. And compared with homogeneous simple materials, these materials have a high work hardening rate, and increased specific strength and hardness, and a good balance between the strength and the ductility. They have an application in transportation, an automotive and aerospace sector. In the end, I'd like to thank my PhD advisor, Professor Dave McDowell, and my postdoc advisor, Professor Irene Byron, as well as my collaborators all over the world. I also would like to thank the financial support from the Office of the Labor Research Department of Energy and the National Science Foundation. And finally, I'd like to thank Professor Farouk Mistry for inviting me. And that's the end of my talk. And thank you very much for your time. Please let me know if you have any questions.
All right. Well, thank you so much, Dr. Xu. That was a really interesting talk. We're going to go ahead and open up the floor for questions. As a reminder, we do have these sign-up sheets that have been posted in chat. If you could take a minute and just write on that so that we know who attended. And I will open up to anyone who would like to ask Dr. Xu a question.
I want to ask some questions. May I?
Okay, sure.
My name is Taozhe Li, and I want to ask you, you say you use machine learning to process problems. It will be more and more useful in your research, right? I want to know that, you know, the problem of some machine learning algorithms, there has some drawbacks, sounds like explainable. You know, it's hard to explain why the results like this. Would this affect your research? Would this drawbacks affect your research?
I would say yes, because a common practice in my field, I believe, what the people usually do is that they would apply multiple machine learning model to the same problem, and they will choose one that works the best.
Okay, that's my problem. Appreciate. Thank you for your answering.
I had a question. So I mean, you talked about some of these, I think nanometer thin superlattices sort of things where one metal is stacked over another metal, but the thicknesses is like just nanometers. But I know that you're looking at mechanical properties, but I think in the thermoelectrics field, I think if you may know, people are looking at such superlattices and alloys because as you said, like they stack differently. So sometimes they stack over each other, and then there is some dislocation or mismatch in lattice, which helps in the thermoelectric properties of certain alloys as well. So have you done in are you interested in that specific field, or do you want to just look at mechanical properties for now? Because that is something that we are also interested in, is looking at the thermal properties of such superlattices, and then like altogether knowing about mechanical as well as thermal properties of such material systems.
Yeah, so that's a very good question. So overall, I think I'm interested in a multi-scale or multi-physics simulation, right? So by multi-physics, I mean, of course, it's not just the mechanical property, but the other types of property as well. However, I would add that my the method and I have used so far can only solve can only be used to address the mechanical
properties.
Right. But I do hope that my method can be somehow extended to involve other types of property as well.
Right, because in our lab, I mean, previously one of our lab mates used to do simulations on thermal properties. So we would use density functional theory to calculate cell parameters, and then we would use these cell parameters and solve the Boltzmann transport equation to get the thermal properties of material systems like superlattices is something we want to do, is do the simulation because we have the experimental capability. And so combining both simulation and experiment, we could do like validation of these results. So that's why I asked, because if we can do that, then there's a certain collaboration that we could see for sure. Yes, that's why
So,
I was interested in that specifically.
So I believe that you can study the thermal property of the material using either the DFT or the MD simulation.
MD
right?
simulations, yes.
You
Right.
need somebody, do the do like do those type of simulation. I believe that's something my lab can do.
Sure, sir. Then I think it would be nice to have a chat with you later after this, so
Okay.
I can figure that out. Thank you so much. Thanks.
I have a small question here. So we have the body, like if this is my solid body and I'm applying some force here. So this macro force are we modeling that in terms of atomic force also? Like the macro force, are we modeling that in the atomic level while modeling it atomic plus macro scale level? Or we need to scale it down or something like that?
Okay, so my research, I think, works at a pretty small scale. So, so can you repeat your question?
So it is like if a body is moving,
Okay.
so that it is having some inertia force. Can we model that inertia force while modeling it with CAC?
And I don't think so. And yeah, I think that the method I worked on is only applied to a material under certain types of deformation. Yeah, and if the objects just move as a whole, if it's not deformed in any way, I don't think we can do that.
Thank you.
I kind of had a question regarding the machine learning a little bit more.
Okay.
So when I've talked to other material scientists about using machine learning, a big worry for them was kind of like getting both enough data and data in the right format to do machine learning on. And I know also this kind of depends on what kind of model you're using. For example, I think you can do like pretty good machine learning with basic kind of regression models, but if you're doing something more complex like deep learning, it's required to have a whole lot of data. And I'm just kind of wondering, have you had difficulties in getting enough data to do this kind of learning on, or getting it in the proper format? And how do you go about that?
Yeah, so that's really depends on where you obtain the data. If you obtain data from the modeling and the simulation, I think it would be relatively easy to generate a lot of data. But if you obtain data from the experiment, then I think so usually there are very few and experiment and whole data out there. And in terms of the format, I don't think I ever run into that problem. You just need to make some code, right?
Okay. So you just kind of use, I guess, just like synthetic data from simulations to kind of feed your models?
Right.
Okay. Do you ever have any worries about, I guess, validation and making sure that it's accurate if it's being trained on synthetic data?
Not yet. Not in my previous work, but maybe that's something I need to think about in the future as I spend more time on machine learning.
Hmm. Thank you. Do we have any further questions from Dr. Zhu? All right, then. If we have no further questions, thank you so much, Dr. Zhu, for giving this presentation today. If anybody comes up with anything they'd like to ask later, feel free to email. And thank you all so much for attending. One last reminder to sign in to the sign up sheet that is in the chat currently if you haven't yet. And thank you so much.
Okay. Thank you, everyone.